This is the video on mass versus weight. So remember, in these videos, there will be two codes. One will be a written code that'll pop up on the screen. The other code will be a code said by myself, a verbal code. Each code will be 3 numbers, and you will need those codes in order to move on with any homework assignment. So remember, when you're watching these screens, what's in green is important. You can make a nice little bulleted list of the big ideas from what comes up on the screen. So green is that important color to write down. So here is the weekly review video. This is the written code. I would recommend you write this down somewhere. All right, so here's just a quick idea, right? So when dropped, what will hit the ground first, a penny or a tissue paper? So just think about that. Think about dropping a penny and dropping a tissue paper. So let's see, what would you need to know? Like if it were to hit the ground, they would both hit the ground at the same time in a vacuum. Now, you'd probably look at this and go, well, obviously, the penny's going to hit the ground first because it's heavier. It will hit the ground first, but not because it's heavier. All objects accelerate down at the same rate on that same planetary body. The reason why it hits the ground first is because, well, that the air resistance is what slows that tissue paper down. If we were to just remove the air from that equation, they would both accelerate down at the same rate. So there's like videos out there. You can see a picture of like somebody dropping a bowling ball and feathers inside of a vacuum chamber where there is no air, and they will accelerate down at the same rate. So you can do that tissue paper and penny demo by placing the tissue paper and penny on top of a large like textbook and drop it. That'll push the air out of the way, and you'll see that the penny and the tissue paper will accelerate down at the same rate. So what does this have to do with what we're learning? This is the original question. What is the difference between mass and weight? So mass is the measure of the amount of stuff in an object. We measure it in kilograms. It does not depend on location. It is closely related to inertia. Inertia is another topic we're going to learn about when we get to Newton's laws. It cannot be measured directly, and it has only a magnitude, which makes it a scalar quantity. So that brings us to weight. Weight is the measure of the force of gravity on an object. We measure weight in newtons. It can change with location. It is closely related to gravity. It can be measured directly with the scale. It has both direction and magnitude, which makes it a vector quantity. So what does it mean that weight is closely related to gravity and can change with location? So gravity depends on the mass of the body a person is standing on. If you were to go to the moon or another planet, your weight would also change. Now, I like this graphic up here. So if you look at an astronaut, mass, 100 kilograms, that's just the measure amount of stuff that makes up that astronaut. Now, if that astronaut were to go to the moon, to Mars, or in just space, that does not change the amount of stuff that that astronaut is made out of. Now, if that astronaut were to go to the moon, then yes, the gravitational pull on that astronaut would change. The weight would change, but the amount of stuff that that astronaut is made out of does not. So there is also this photo that I took. This is at the Hayden Planetarium in New York. They have these scales all over the ground, and you can step on them, and they would show you how much you would weigh on different planetary bodies. And you can see this one, I'm standing on the one that says, what you would weigh on the moon. I'd weigh about 27.8 pounds. But if I went to the moon, well, that wouldn't change the amount of stuff that I'm made out of. That would not change my mass, but it would change my weight, the gravitational pull on me. So gravity is a force of attraction between any two masses. Gravity pulls masses towards the center of the Earth. That's why it's a vector quantity, because it is a force. The direction just happens to always be down no matter where you're standing. Now, it is not only attraction between an object and an Earth, right? It's the attraction between all masses in the universe. So you, me, like if you just have mass, gravity, you do have a gravitational pull. Now, it would be very small compared to something like the Earth or the moon, but you do because you are made out of mass. So let's take a look at how we calculate these and put all of these together. So the more mass an object has, the more gravitational force. The sun's gravity keeps the Earth in orbit. The moon's gravity pulls on the Earth and makes the tides rise and fall every day. Now, when we're calculating, this is the equation to calculate weight. Weight equals mass times the strength of gravity. Now, on Earth, we use gravity as 9.8 meters per second squared. We measure the strength of gravity on that planetary body based on how the acceleration of objects falling on that planet. On Earth, 9.8 meters per second squared. That's how fast that penny was falling. That's how fast that tissue paper was falling when I put a book underneath it. That is the gravitational strength of Earth, and we just use the G, like G. So that's the equation to calculate weight. Force of gravity, and you notice it's F G, like lower, like subscript G. The reason why we don't use W later in another topic is work that we're going to learn about. That's why we don't use W. We use force of gravity because that is what weight is. So there's the equation, and that's the triangle that you can use if you're searching to find out how to calculate either of them. So let's just use these to calculate it. So here's a problem that you can get. An astronaut has a mass of 60 kilograms. What is the weight of the astronaut on Earth? So in order to answer, we have to say, well, what is it asking us to find? I mean, we're asked to be able to find the weight, the force of gravity on planet Earth. Now, we know the gravitational strength on Earth is 9.8 meters per second squared, and the mass is given to us. So what we do is we plug that into the equation. We get 60 kilograms times 9.8 meters per second squared, and you get 588 newtons. So let's do another problem. So a book is sitting on the table on Earth, has a weight of 19.6 newtons. What is the mass of the book? So this question is asking us to find the mass. So in this triangle, we cover up mass, and we get the force of gravity, or the weight, divided by the strength of gravity. So the weight is 19.6 newtons, and the strength of gravity, like it says on Earth, 9.8 meters per second squared. So all I do is I plug that in, and I get 2 kilograms. So let's do another kind of problem. So let's just say that same astronaut that we looked at in problem number 1, has a mass of 60 kilograms, has a weight of 96 newtons on the moon. What is the strength of gravity on the moon? So in this one, we're being asked to find the strength of gravity. Now, we're not on Earth anymore, so we just don't use 9.8 meters per second squared. Notice that astronaut is still 60 kilograms, right? That does not change the amount of stuff that astronaut is made out of. So what I do is I take the weight, the force of gravity, divided by the mass, and what I'm going to get is 1.6 meters per second squared. Notice that's a lot less than the strength of gravity on Earth, right? Because the moon is smaller. It has a smaller gravitational pull. So how much do you weigh on other planets? So in order to answer this question, we did a class activity. You can see that where you clicked on a planet and it gave you the mass, you had the mass of that astronaut and it gave you the weight, and you were to calculate the strength of gravity. So at this time, I'll go ahead and give you the verbal code. The verbal code is 332. I say that again, the verbal code is 332. So then the last thing we did was we found mass versus weight, where I gave you 3 different masses with the mass on them, and you found the weight using a spring scale, and we were able to calculate the strength of gravity on planet Earth. Like, we knew that, but this just helped us reinforce that idea. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.